Learning objectives. In this chapter, the user will learn the following in detail. Information theoretic argument, adversary argument, P and NP, NP completeness and reduction, primality tests, quadratic residues, applications to cryptography, lower bound theory, and information theoretic bounds. Adversary argument. Adversary argument is a method of proving a lower bound by playing role of adversary that makes algorithm work the hardest by adjusting input. Example, guessing a number between 1 and n with yes or no questions. Adversary puts the number in a larger of the two subsets generated by last question. What is an adversary? It is an algorithm which intercepts access to data structures, constructs the input data only as needed, attempts to make original algorithm work as hard as possible, analyze adversary to obtain lower bound. Important restriction. Although data is created dynamically, it must return consistent results. If it replies that x of 1 is less than x of 2, it can never say later that x of 2 is less than x of 1. Max and min. Keep values and status codes for all keys. Codes. N represents never used. W represents won once but never lost. L represents lost once but never won. WL represents won and lost at least once. Key values will be arranged to make answers to come out right. Accumulating information. 2n. 2 bits of information are required to solve the problem. All keys except one must lose. All keys except one must win. Comparing n pairs gives n by 2 comparisons and n bits of information. N minus 2 additional bits are required. One comparison each is needed. Results. 3n by 2 minus 2 comparisons are needed. This is a lower bound. Upper bound is given by the following. Compare elements pairwise but losers in one pile, winners in another pile. Find max of winners, min of losers. This gives 3n by 2 minus 2 comparisons. The algorithm is optimal. Largest and second largest. Second largest must have lost to largest. Second largest is max of those compared to largest. Tournament method gives n minus 1 plus log n comparisons for finding largest and second largest. Second largest adversary. All keys are assigned weights W of I. Weights are all initialized to 1. Adversary replies are based on weights. Accumulation of weight. Solution of the problem requires all weight to be accumulated with one key. All other keys must have weight 0. Since weight accumulates to highest weight, weight can at most double with each comparison. Log n comparisons are required to accumulate all weight. Results. The largest key must be compared with log n other keys. Finding the second largest requires at least log n comparisons after finding the largest. This is a lower bound. The tournament algorithm is optimal. Applications to cryptography. Cryptographic computations. The Internet is enabling a growing number of activities such as correspondence, example email, shopping, example web stores, and financial transactions, example online banking, to be performed electronically. However, the Internet itself is an insecure transmission network. Data transmitted over the Internet travels through several intermediate specialized computers called routers, which can observe the data and potentially modify it. A variety of cryptographic techniques have been developed to support secure communication over an insecure network such as the Internet. Cryptography research has developed the following useful cryptographic computations. Encryption and decryption. A message M to be transmitted, called the plain text, is transformed into an unrecognizable string of characters C, called the ciphertext, before being sent over the network. This transformation is known as encryption. After the ciphertext C is received, it is converted back to the plain text M using an inverse transformation that depends on additional secret information. This reverse transformation is called decryption. An essential ingredient in encryption is that it should be computationally infeasible for an outsider to transform C back to M without knowing the secret information possessed by the receiver. Digital signatures. The author of a message M computes a message S that is derived from M and secret information known by the author. The message S is a digital signature if another party can easily verify that only the author of M would have computed S in a reasonable amount of time. Using cryptographic computations for information security services. Data integrity. Computing a digital signature S of a message M not only helps us to determine the author of M, it also verifies the integrity of M. For a modification to M would produce a different signature. So, to perform a data integrity check, we can perform a verification test that S is, in fact, a digital signature for the message M. Authentication. The above cryptographic tools can be used for authentication in two possible ways. In password authentication schemes, a user will type a user ID and password in a client application, with this combination being immediately encrypted and sent to an authenticator. If the encrypted user ID and password combination matches that in a user database, then the individual is authenticated, and the database never stores passwords in plain text. Alternatively, an authenticator can issue a challenge to a user in the form of a random message M that the user must immediately digitally sign for authentication. Authorization. Given a scheme for authentication, we can issue authorizations by keeping lists called access control lists that are associated with sensitive data or computations that should be accessed only by authorized individuals. Alternatively, the holder of a right to sensitive data or computations can digitally sign a message C that authorizes a user to perform certain tasks. For example, the message would be of the form, I, US Corporation Vice President, give person X permission to access our fourth quarter earnings data. Confidentiality. Sensitive information can be kept secret from non-authorized agents by encrypting it. Non-repudiation. If we make the parties negotiating a contract, M, digitally sign that message, then we can have a way of proving that they have seen and agreed to the content of the message M. This section gives an introduction to cryptographic computations. Conventional names of persona, such as Alice, Bob, and Avi, are used to denote the parties involved in a cryptographic protocol. Symmetric encryption schemes. A fundamental problem in cryptography is confidentiality, that is, sending a message from Alice to Bob so that a third-party AV cannot gain any information from an intercepted copy of the message. Moreover, we have observed that confidentiality can be achieved by encryption schemes or ciphers, where the message M to be transmitted, called the plain text, is encrypted into an unrecognizable string of characters C, called the ciphertext, before being sent over the network. After the ciphertext C is received, it is decrypted back to the plain text M using an inverse transformation called decryption. Secret keys. In describing the details of an encryption scheme, we must explain all the steps needed in order to encrypt a plain text M into a ciphertext C, and how to then decrypt that ciphertext C back to M. Moreover, in order for Evie to be unable to extract M from C, there must be some secret information that is kept private from her. In traditional cryptography, a common secret key, K, is shared by Alice and Bob and is used to both encrypt and decrypt the message. Such schemes are also called symmetric encryption schemes, since K is used for both encryption and decryption, and the same secret is shared by both Alice and Bob. Substitution ciphers. A classic example of a symmetric cipher is a substitution cipher, where the secret key is a permutation pi of the characters of the alphabet. Encrypting plain text M into ciphertext C consists of replacing each character x of M with character y equals pi of x. Decryption can be easily performed by knowing the permutation function pi. Indeed, M is derived from C by replacing each character y of C with character x equals pi minus 1 into y. The Caesar cipher is an early example of a substitution cipher, where each character x is replaced by character y equals x plus k mod n, where n is the size of the alphabet and k lies between 1 and n, is the secret key. This substitution scheme is known as the Caesar cipher, for Julius Caesar is known to have used it with k equals 3. Substitution ciphers are quite easy to use, but they are not secure. Indeed, the secret key can be quickly inferred using frequency analysis based on the knowledge of the frequency of the various letters or groups of consecutive letters in the text language. The one-time pad. Secure symmetric ciphers exist. Indeed, the most secure cipher known is a symmetric cipher. It is the one-time pad. In this crypto system, Alice and Bob each share a random bit string K as large as any message they might wish to communicate. The string K is the symmetric key for to compute a ciphertext C from a message M. Alice computes C equals M circle plus K, where circle plus denotes the bitwise exclusive OR or XOR operator. She can send C to Bob using any reliable communication channel, even one on which Evie is eavesdropping, because the ciphertext C is computationally indistinguishable from a random string. Nevertheless, Bob can easily decrypt the ciphertext message C by computing C circle plus K, since C circle plus K produce M, where 0 denotes the bit string of all zeros the same length as M. This scheme is clearly a symmetric cipher system, since the key K is used for encryption and decryption. The one-time pad is computationally efficient for bitwise exclusive OR, is one of the fastest operators that computers can perform. Also, as already mentioned, the one-time pad is incredibly secure. Nevertheless, the one-time pad crypto system is not widely used. The main trouble with this system is that Alice and Bob must share a very large secret key. Moreover, the security of the one-time pad depends crucially on the fact that the secret key K is used only once. If K is reused, there are several simple crypto analyses that can break this system. For practical crypto systems, we prefer secret keys that can be reused and are smaller than the messages they encrypt and decrypt. Other symmetric ciphers. Secure and efficient symmetric ciphers do exist. They are referred to by their acronyms or colorful names such as triple DES, IDEA, Blowfish, and Reindoll. They perform a sequence of complex substitution and permutation transformations on the bits of the plain text. While these systems are important in many applications, they are only mildly interesting from an algorithmic viewpoint. They run in time proportional to the length of the message being encrypted or decrypted. Public key cryptosystems. A major problem with symmetric ciphers is key transfer, or how to distribute the secret key for encryption and decryption. In 1976, Diffie and Hellman described an abstract system that would avoid these problems, the public key cryptosystem. While they didn't actually publish a particular public key system, they discussed the features of such a system. Specifically, given a message M, encryption function E, and decryption function D, the following four properties must hold. Property 1, D of E of M equals M. Property 2, both E and D are easy to compute. Property 3, it is computationally infeasible to derive D from E. Property 4, E of D of M equals M. The first property states that once a message has been encrypted, applying the decryption procedure will restore it. Property 2 is perhaps more obvious. In order for a cryptosystem to be practical, encryption and decryption must be computationally fast. The third property is the start of the innovation. It means that E only goes one way. It is computationally infeasible to invert E unless you already know D. Thus, the encryption procedure E can be made public. Any party can send a message while one knows how to decrypt it. If the fourth property holds, then the mapping is 1-to-1. Thus, the cryptosystem is a solution to the digital signature problem. Given an electronic message from Bob to Alice, how can we prove that Bob actually sent it? Bob can apply his decryption procedure to some signature message M. Any other party can then verify that Bob actually sent the message by applying the public encryption procedure E. Since only Bob knows the decryption function, only Bob can generate a signature message which can be correctly decoded by the function E. Public key cryptography is the basis of modern cryptography. Its economic importance is fast growing, since it provides the security infrastructure of all electronic transactions over the Internet. The design of public key cryptosystems can be described in general terms. The idea is to find a very tough problem in computer science and then somehow tie the cryptosystem to it. Ideally, one arrives at an actual proof that breaking the cryptosystem is computationally equivalent to solving the difficult problem. There is a large class of problems called NP-complete, which do not have known polynomial time algorithms for their solution. In fact, it is widely believed that there are none. Then, to generate the particular encryption and decryption keys, we create a particular set of parameters for this problem. Encrypting then means turning the message into an instance of the problem. The recipient can use secret information, the decryption key, to solve the puzzle effortlessly. The RSA cryptosystem. Some care must be taken in how a computationally difficult problem is tied to a cryptosystem. One of the earlier public key cryptosystems, the Merkle-Hellman system, linked encryption to something called the knapsack problem, which is NP-complete. The problems the system generates turn out to be a special subclass of the knapsack problem that can be easily solved. So, designing public key cryptosystems has its share of subtleties. Probably the most well-known public key cryptosystem is also one of the oldest and is tied to the difficulty of factoring large numbers. It is named RSA after its inventors Rivest, Shamir, and Adelman. In this cryptosystem, we begin by selecting two large primes, P and Q. Let n equals P into Q, be their product and recall that phi of n equals p minus 1 into q minus 1. Encryption and decryption keys E and D are selected so that E and phi of n are relatively prime. E into D is equivalent to 1 mod phi of n. The second condition means that D is the multiplicative inverse of E mod phi of n. The pair of values n and E form the public key while D is the private key. In practice, E is chosen either randomly or as one of the following numbers 3, 17 or 65, 537. The rules for encrypting and decrypting with RSA are simple. Let us assume, for simplicity, that the plain text is an integer m with m lies between 0 and n. If m is a string, we can view it as an integer by concatenating the bits of its characters. The plain text m is encrypted into ciphertext C with one modular exponentiation using the encryption key E as the exponent. C gets m power E mod n RSA encryption. The decryption of ciphertext C is also performed with an exponentiation using now the decryption key D as the exponent. M gets C power D mod n RSA decryption. The correctness of the above encryption and decryption rules is justified by the following theorem. Theorem: let P and Q be two odd primes and define n equals PQ. Let E be relatively prime with phi of n and let D be the multiplicative inverse of E modulo phi of n for each integer x such that x lies between 0 and n, x power ed equivalent to x mod n. Proof: let y equals x power ed mod n. We want to prove that y equals x. Because of the way we have selected E and D, we can write ed equals k phi of n plus 1 for some integer k. Thus we have y equals x k phi of n plus 1 mod n. We distinguish two cases. Case 1. X does not divide n. We rewrite y as follows. By Euler's theorem, we have x power phi of n mod n equals 1, which implies y equals x and 1 power k mod n equals x. Case 2. X divides n. Since n equals pq with p and q primes, x is a multiple of either p or q. Suppose x is a multiple of p, that is x equals hp for some positive integer h. Clearly, x cannot be a multiple of q as well, since otherwise x would be greater than n equals pq, a contradiction. Thus, GCD of x, q equals 1, and by Euler's theorem, we have x power phi of q equivalent to 1 mod q. Since phi of n equals phi of p into phi of q, raising both sides of the above congruence to the power of k phi of q, we obtain x power k phi of n equivalent to 1 mod q, which we rewrite as x power k phi of n equals 1 plus iq for some integer I, multiplying both sides of the above equality by x and recalling that x equals hp and n equals pq, we obtain the following result. Thus we have y equals x power k phi of n plus 1 mod n, which is equals x. In either case, we have shown that y equals x, which concludes the proof of the theorem. Using RSA for digital signatures. The symmetry of the encryption and decryption functions implies that the RSA crypto system directly supports digital signatures. Indeed, a digital signature S for message M is obtained by applying the decryption function to M, that is, S gets m power d mod n RSA signature. The verification of the digital signature S is now performed with the encryption function, that is, by checking that M equivalent to S power E mod n RSA verification. The difficulty of breaking RSA. Note that even if we know the value E, we cannot figure out D unless we know phi of n. Most cryptography researchers generally believe that breaking RSA requires that we compute phi of n and that this requires factoring n. While there is no proof that factorization is computationally difficult, a whole series of famous mathematicians have worked on the problem over the past few hundred years. Especially if n is large, approximately equal to 200 digits, it will take a very long time to factor it. To give you an idea of the state of the art, mathematicians were quite excited when a nationwide network of computers was able to factor the ninth Fermat number 2 power 512 minus 1. This number has only 155 decimal digits. Barring a major breakthrough, the RSA system will remain secure. If technology somehow advances to a point where it is feasible to factor 200-digit numbers, we need only choose an n with 3 or 400 digits. Analysis and setup for RSA encryption. The running time of RSA encryption, decryption, signature, and verification is simple to analyze. Indeed, each such operation requires a constant number of modular exponentiations, which can be performed with method fast exponentiation. Computational complexity. Two types of complexities. One is time complexity and another one is space complexity. By time or space complexity, we mean the time or space as a function of input size required by an algorithm to solve a problem. In study of algorithms, prove by giving and analyzing an algorithm that can be solved in a big O of f of n time for some function f of n that we try to reduce as much as possible. On the other hand, in complexity theory, we try to find a function g of n as large as possible for which we prove that any algorithm solves problem on all its in big omega of g of n function. G of n is called lower bound and the complexity of the problem. The principal techniques and concepts. Information theoretic argument, adversary argument, reduction, and NP completeness. Information theoretic bounds. Entropy basics. Let omega be a finite set and P a probability distribution on omega. The entropy of a random variable x distributed according to P is defined as follows. Entropy is a means to quantify the amount of uncertainty in a distribution. If the distribution is focused on a single element, the entropy is 0. For the uniform distribution on omega, the entropy is maximal at log mod omega. These examples set the bounds for the range of entropy. H of x lies between 0 and log mod omega. Entropy can also be interpreted in terms of compression. Shannon's source coding theorem states that the optimal expected code word length of elements of a random variable x is the entropy of x. Make use of the conditional entropy. First consider conditioning on a single outcome as shown in below figure. This quantity can actually be larger than h of x. Imagine the case where x equals random bit if y equals 0, 0 if y equals 1. Then h of x less than 1, yet h of x given y equals 0, which is equals 1. The conditional entropy is the expectation of the last quantity over y. H of x given y equals entropy y of h x given y equals y, which is less than or equals h of x. This quantity is at most the entropy of x. Finally, let the joint entropy of x, y be h of x y equals h of x plus h of y given x. Mutual information. For lower bounds, we will use mutual information For two random variables z, pi, this is defined as follows. In applications to communication complexity, typically z will be a distribution over inputs x into y and pi will be a distribution over protocol transcripts. To see how this can work to show lower bounds, let us look at a warm-up example, the index function. The index function is defined as index 0,1 power n into n gives 0,1, where index of x, I equals xi. Consider the one-way complexity of the index function from Alice to Bob. Let pi of x, r be a random variable over the messages of Alice, which depends on the distribution x over Alice's input and r random coins of Alice. Notice that h of pi will be a lower bound on the maximum length of a message of Alice. We will actually lower bound the potentially smaller quantity I of x pi. Use the uniform distribution over Alice's inputs. Then we have as follows. Now it remains to upper bound h of x given pi using the fact that h of y, z equals h of y plus h of z given y. We have h of x given pi less than or equals summation j h of xj given pi. As we are dealing with one-way communication, conditioning on a particular input to Bob does not change Alice's action. Thus we have h of xj given pi equals h of xj given pi, b equals j. That is, given that Bob's input is actually j. Finally, we have by correctness of the protocol that this entropy must be small, at most h of epsilon if the error probability is epsilon. Putting everything together, we have as shown below. Information theoretic argument. This technique applies to problems involving comparisons. Useful definitions. One way to represent working of an algorithm is a decision tree or binary rooted tree. Binary tree of height k has at most 2 power k leaves. Each interval node of the decision tree contains a test on the data. Each leaf or verdict contains an input. Conversely, any such decision tree can be thought of as an algorithm. Decision tree can also be used to analyze the complexity of a problem on the average rather than in the worst case. The complexity of comparison-based sorting. Problem 1. What is the minimum number of comparison needed to sort n items? A decision tree is a labeled directed binary tree. Each internal node contains a comparison between two of the elements to be sorted. Each leaf contains an ordering of the elements. Given a total order relation between the elements, a trip through the tree consists of starting from the root and asking oneself the question that is found there. If the answer is yes, the trip continues recursively in the left-hand subtree. Otherwise, it continues recursively in the right-hand subtree. The trip ends when it reaches a leaf. This leaf contains the verdict associated with the order relation used. A decision tree for sorting n elements is valid if to each possible order relation between the elements, it associates a verdict that is compatible with this relation. Finally, a decision tree is pruned if all its leaves are accessible from the root by making some consistent sequence of decisions. The following problem will help you grasp these notions. Problem 2. Verify that the decision tree given in below figure is valid for sorting 3 elements A, B and C. Every valid decision tree for sorting n elements gives rise to an ad hoc sorting algorithm for the same number of elements. The following figure shows an algorithm to the above decision tree. Similarly, to every deterministic algorithm for sorting by comparison that corresponds for each value of n, a decision tree that is valid for sorting n elements. The below figure shows the tree corresponding to the insertion sorting algorithm when 3 elements are to be sorted. The below figure shows the tree corresponding to the heap sort algorithm when 3 elements are to be sorted. Notice that heap sort sometimes makes unnecessary comparisons. For instance, if B is less than or equals A, which is less than C, the decision tree of heap sort first tests whether B is a greater than A. Answer, no. And then whether C is greater than A. Answer, yes. It would now be possible to establish the correct verdict, but it nonetheless asks again whether B is greater than A before reaching its conclusion. Thus, heap sort is not optimal. This situation does not occur with the decision tree of figure of insertion sort, but beware of appearances. It occurs even more frequently with the insertion sorting algorithm than with heap sort when the number of elements to be sorted increases. Problem 3. Give the pruned decision trees corresponding to the insertion sorting algorithm and to heap sort for the case of 4 elements. The height of the pruned decision tree corresponding to any algorithm for sorting n elements by comparison, that is, the distance from the root to the most distant leaf, gives the number of comparisons carried out by this algorithm in the worst case. For example, a possible worst case for sorting 3 elements by insertion is encountered if the array is already sorted into descending order. C is less than B and B is less than A. In this case, the 3 comparisons B less than A, C less than A and C less than B, situated on the path from the root to the appropriate verdict in the decision tree, all have to be made. The decision trees for sorting 3 elements are all of height 3. Can we find a valid decision tree for sorting 3 elements whose height is less? If so, we shall have an ad hoc algorithm for sorting 3 elements that is more efficient in the worst case. Try it. You will soon see that this cannot be done. We now prove more generally that such a tree is impossible. Lower bound theory. Lower bound is an estimate of a number of operations needed to solve a given problem. Tight lower bound. There exists an algorithm with the same efficiency as the lower bound. Examples are shown in this table. Methods of establishing lower bounds. Trivial lower bounds. Sorting. Information theoretic arguments. Decision trees. Any comparison sorting algorithm that is bubble sort. A convenient model of algorithms involving comparisons like sorting. Internal nodes represent comparisons. Leaves represent outcomes. Adversary arguments. Merging 2 sorted lists. It's a game between the adversary and the unknown algorithm. The adversary has the input and the algorithm asks questions to the adversary about the input. The adversary tries to make the algorithm work the hardest by adjusting the input consistently. It wins the game after the lower bound time, lower bound proven, if it is able to come up with 2 different inputs. Searching in a sorted list. Objective: A of 1 lesser than A of 2, it goes up to A of n. Examples: comparison-based search algorithms, search list by comparing target element with list elements, sequential search, order n, binary search, order log square n. Comparison tree is shown in below figure. Let us denote dB of n be the worst case for best algorithm. dB of n equals highest of the best tree, which is equal to shortest highest of trees. Each node will have n nodes. Lemma: a tree of nodes and height h, then h greater than or equals ceiling of log of n plus 1 minus 1. Then dB of n greater than or equals ceiling of log n plus 1 minus 1. Finding the minimum and maximum. Let us consider the complexity of finding the largest and smallest elements. More formally, given a sequence x equals x1 up to xn of n distinct numbers, find indices I and j such that xi equals min of x and xj equals max of x. How many comparisons do we need to solve this problem? An upper bound of 2n minus 3 is easy. Find the minimum in n minus 1 comparisons and then find the maximum of everything else in n minus 2 comparisons. Similarly, a lower bound of n minus 1 is easy since any algorithm that finds the min and the max certainly finds the max. We can improve both the upper and lower bound to ceiling of 3n by 2 minus 2. The upper bound is established by the following algorithm. Compare all ceiling of n by 2 consecutive pairs of elements x 2i minus 1 and x 2i. Put the smaller element into a set S. Put the larger element into a set L, and if n is odd, put xn into both L and S. Then find the smallest element of S and the largest element of L. The total number of comparisons is at most. Ceiling of n by 2 builds S and L. Ceiling of n by 2 minus 1, compute min S. Ceiling of n by 2 minus 1, compute max L. Ceiling of n by 2 plus ceiling of n by 2 minus 1 plus ceiling of n by 2 minus 1 equals ceiling of 3n by 2 minus 2. Sorting. Decision tree for sorting 3 elements are shown in below figure. To find the lower bound, we have to find the smallest depth of a binary tree. We have n factorial distinct permutations, n factorial leaf nodes in the binary decision tree. The balanced tree has the smallest depth, which is the lowest bound for sorting. Ceiling of log n factorial equals big omega of n log n. Method 1 is shown in below figure. Lower bound for sorting big omega of n log n. Method 2 using Stirling approximation as shown in below figure. Merging two sorted lists. Merge two sorted sequences A and B with lengths m and n. Binary decision tree. There are m plus n, c, n leaf nodes in the binary tree. There are m plus n, c, n ways. So the lower bound for merging, ceiling of log m plus n c n less than or equals m plus n minus 1, conventional merging. When m equals n, log of m plus n c n is shown in below. Using Stirling approximation, the log of m plus n c n approximately equal to big omega of n. NP completeness and reduction. NP completeness and reducibility. Perhaps the most compelling reason why theoretical computer scientists believe that P is not equals NP comes from the existence of the class of NP-complete problems. This class has the intriguing property that if any NP-complete problem can be solved in polynomial time, then every problem in NP has a polynomial time solution that is P equals NP. Despite years of study, though no polynomial time algorithm has ever been discovered for any NP-complete problem, the language Ham cycle is one NP-complete problem. If we would decide Ham cycle in polynomial time, then we would solve every problem in NP in polynomial time. In fact, if NP minus P should turn out to be non-empty, we would say with certainty that Ham cycle belongs to NP minus P. The NP-complete languages are, in a sense, the hardest languages in NP. We shall show how to compare the relative hardness of languages using a precise notion called polynomial time reducibility. Then, we formally define the NP-complete languages, and we finish by sketching a proof that one such language called circuit SAT is NP-complete. Reducibility. Intuitively, a problem Q can be reduced to another problem Q dash if any instance of Q can be easily rephrased as an instance of Q dash. The solution to which provides a solution to the instance of Q. For example, the problem of solving linear equations in an indeterminate X reduces to the problem of solving quadratic equations. Given an instance ax plus b equals 0, we transform it to 0x squared plus ax plus b equals 0, whose solution provides a solution to ax plus b equals 0. Thus, if a problem Q reduces to another problem Q dash, then Q is, in a sense, no harder to solve than Q dash. Returning to our formal language framework for decision problems, we say that a language L1 is polynomial time reducible to a language L2. Return L1 polynomial time reduction L2 if there exists a polynomial time computable function f 0,1 star implies 0,1 star such that for all x belongs to 0,1 star, x belongs to L1 if and only if f of x belongs to L2. The function f is the reduction function and polynomial time algorithm f that computes f is a reduction algorithm. The following figure illustrates the idea of a polynomial time reduction from a language L1 to another language L2 via a reduction function f. For any input x belongs to 0,1 star, the question of whether x belongs to L1 has the same answer as the question of whether f of x belongs to L2. Each language is a subset of 0,1 star. The reduction function f provides a polynomial time mapping such that if x belongs to L1, then f of x belongs to L2. Moreover, if x does not belong to L1, then f of x does not belong to L2. Thus, the reduction function maps any instance x of the decision problem represented by the language L1 to an instance f of x of the problem represented by L2. Providing an answer to whether f of x belongs to L2 directly provides the answer to whether x belongs to L1. Polynomial time reductions give us a powerful tool for proving that various languages belongs to P. NP completeness, NPC. Polynomial time reductions provide a formal means for showing that one problem is at least as hard as another to within a polynomial time factor. That is, if L1 polynomial time reduction L2, then L1 is not more than a polynomial factor harder than L2, which is why the less than or equal to notation for reduction is mnemonic. We can now define the set of NP-complete languages, which are the hardest problems in NP. A language L is a subset of 0,1 star is NP-complete if 1. L belongs to NP and 2. L dash polynomial time reduction L for every L dash belongs to NP. If a language L satisfies property 2 but not necessarily property 1, we say that L is NP hard. Also define NPC to be the class of NP-complete languages. As the following theorem shows, NP-completeness is at the crux of deciding whether P is in fact equal to NP. Theorem: if any NP-complete problem is polynomial time solvable, then P equals NP. Equivalently, if any problem in NP is not polynomial time solvable, then no NP-complete problem is polynomial time solvable. Proof: suppose that L belongs to P and also that L belongs to NPC. For any L dash belongs to NP, we have L dash polynomial time reduction L by property 2 of the definition of NP completeness. Thus, by lemma, which is shown in below figure, we also have that L dash belongs to P, which proves the first statement of the theorem. To prove the second statement, note that it is the contrapositive of the first statement. It is for this reason that research into the P not equals NP question centers around the NP complete problems. Most theoretical computer scientists believe that P not equals NP, which leads to the relationships among P, NP, and NPC. Both P and NPC are wholly contained within NP, and P intersection NPC equals null. Lemma. If L1, L2 is a subset of a set 0, 1 star or languages such that L1 polynomial time reduction L2, then L2 belongs to P implies L1 belongs to P. Proof. Let A2 be a polynomial time algorithm that decides L2 and let F be a polynomial time reduction algorithm that computes the reduction function F. We shall construct a polynomial time algorithm A1 that decides L1. Below figure illustrates how we construct A1. The algorithm F is a reduction algorithm that computes the reduction function F from L1 to L2 in polynomial time, and A2 is a polynomial time algorithm that decides L2. Algorithm A1 decides whether x belongs to L1 by using F to transform any input x into f of x, and then using A2 to decide whether f of x belongs to L. For a given input x belongs to 0, 1 star, algorithm A1 uses f to transform x into f of x, and then it uses A2 to test whether f of x belongs to L2. Algorithm A1 takes the output from algorithm A2 and produces that answer as its own output. The algorithm runs in polynomial time since both f and A2 run in polynomial time. This figure shows relationships among P, NP and NPC. But for all we know, someone may yet come up with a polynomial time algorithm for an NP-complete problem, thus proving that P equals NP. Nevertheless, since no polynomial time algorithm for any NP-complete problem has yet been discovered, a proof that a problem is NP-complete provides excellent evidence that it is intractable. Reduction. Let us consider a decision problem A, which we would like to solve in polynomial time. We call the input to a particular problem an instance of that problem. For example, in path, an instance would be a particular graph G, particular vertices u and v of G, and a particular integer k. Now suppose that we already know how to solve a different decision problem B in polynomial time. Finally, suppose that we have a procedure that transforms any instance alpha of A into some instance beta of B with the following characteristics. The transformation takes polynomial time. The answers are the same. That is, the answer for alpha is yes, if and only if the answer for beta is also yes. We call such a procedure a polynomial time reduction algorithm, and the below figure shows it provides us a way to solve problem A in polynomial time. Way to solve problem A in polynomial time. Given an instance alpha of problem A, use a polynomial time reduction algorithm to transform it to an instance beta of problem B. Run the polynomial time decision algorithm for B on the instance beta. Use the answer for beta as the answer for alpha. As long as each of these steps takes polynomial time, all three together do also, and so we have a way to decide on alpha in polynomial time. In other words, by reducing solving problem A to solving problem B, we use the easiness of B to prove the easiness of A. Recalling that NP completeness is about showing how hard a problem is rather than how easy it is. We use polynomial time reductions in the opposite way to show that a problem is NP complete. Let us take the idea a step further and show how we would use polynomial time reductions to show that no polynomial time algorithm can exist for a particular problem B. Suppose we have a decision problem A for which we already know that no polynomial time algorithm can exist. Suppose further that we have a polynomial time reduction transforming instances of A to instances of B. Now we can use a simple proof by contradiction to show that no polynomial time algorithm can exist for B. Suppose otherwise, that is, suppose that B has a polynomial time algorithm. For NP completeness, we cannot assume that there is absolutely no polynomial time algorithm for problem A. We prove that problem B is NP-complete on the assumption that problem A is also NP-complete. P and NP. The class P is defined as the set of recognition problem for which there exists a polynomial time algorithm where P stands for polynomial time. Thus, P comprises those problems that are formally considered easy. Problems in class P are called tractable. Problems solvable in polynomial time, P time, are considered tractable. The larger problem, class NP, contains the class P. The term NP stands for non-deterministic polynomial and refers to a different hypothetical model of computation which can solve the problems in NP in polynomial time. The class NP consists of all recognition problem with the following property. For any S instance of the problem, there exists a polynomial length certificate or proof of this fact that can be verified in polynomial time. Polynomial time, P time, equals big O of n power k, where n is the input size and k is a constant. NP-complete problems have no known polynomial time solution considered intractable. A decision problem has a yes or no answer. It's different but related to optimization problem, where trying to maximize or minimize the value. For example, consider the problem of determining whether an undirected graph is connected, that is, whether there are paths between every pair of nodes in the graph. This problem's input is a graph G consisting of nodes and edges, and its question is G connected? Notice that most optimization problems are not recognition problems, but most have recognition counterparts. For example, a recognition version of the TSP has as input both a graph G with costs and edges and a number k. The associated question is, does G contain a traveling salesman tour of length less than or equal to k? In general, an optimization problem is not much harder to solve than its recognition counterpart. One can usually embed the recognition algorithm in a binary search over the possible objective function values to solve the optimization problem with a polynomial number of calls to the embedded algorithm. In fact, by reversing the roles played by yes or no, we obtain a problem class known as co-NP. For every recognition problem in NP, there is an associated recognition problem in co-NP obtained by framing the NP question is the negative. Example, do all the traveling salesman tours in G have length greater than k? Many recognition problems are believed to lie outside both of the classes NP and co-NP because they possess no appropriate certificate. Complexity class P. P contains L, which is a subset of 0, 1 star, such that there exists an algorithm A that decides L in P time. Path belongs to P. Complexity class NP. Let A be a P-time algorithm and K is a constant. NP contains L, which belongs to 0, 1 star, such that there exists a certificate Y. Modulus of Y equals big O of modulus of x to the power k, and an algorithm A such that A of x, y equals 1. Subset sum belongs to NP. P versus NP. NP has the ability to appreciate a solution. P has the ability to produce one. P is a subset of NP. Comparing hardness. NP-complete problems are the hardest in NP. If any NP-complete problem is P-time solvable, then all problems in NP are P-time solvable. Primality test. In primality testing, consider the problem of finding large primes. It begins with a discussion of the density of primes. Proceed to examine a plausible but incomplete approach to primality testing, and then present an effective randomized primality test due to Miller and Robin. The density of prime numbers. For many applications, such as cryptography, we need to find large random primes. Large primes are not too rare, so that it is feasible to test random integers of the appropriate size until we find a prime. The prime distribution function pi of n specifies the number of primes that are less than or equal to n. For example, pi of 10 equals 4, since there are 4 prime numbers less than or equal to 10, namely 2, 3, 5 and 7. The prime number theorem gives a useful approximation to pi of n shown in below. The approximation n by ln n gives reasonably accurate estimates of pi of n even for small n. For example, it is off by less than 6% at n equals 10 power 9, where pi of n equals 50, 847, 534 and n by ln n, which is approximately equal to 48, 254, 942. We can view the process of randomly selecting an integer n and determining whether it is prime as a Bernoulli trial. By the prime number theorem, the probability of a success, that is, the probability that n is prime, is approximately 1 by natural logarithm n. The geometric distribution tells us how many trials we need to obtain a success. The expected number of trials is approximately ln n or natural logarithm n. Thus, we would expect to examine approximately ln n integers chosen randomly near n in order to find a prime that is of the same length as n. For example, we expect that finding a 1024-bit prime would require testing approximately ln 2 power 1024 is approximately equal to 710 randomly chosen 1024-bit numbers for primality. Consider the problem of determining whether or not large odd integer n is prime. For notational convenience, assume that n has the prime factorization n equals p1 power e1, p2 power e2, pr power er, where r greater than or equals 1, p1, p2 it goes up to pr are the prime factors of n, and e1, e2 up to er are positive integers. The integer n is prime if and only if r equals 1 and e1 equals 1. One simple approach to the problem of testing for primality is trial division. Dividing n by each integer 2, 3 it goes up to floor of root n. It is easy to see that n is prime if and only if none of the trial divisors divides n. Assuming that each trial division takes constant time, the worst case running time is big theta of square root of n, which is exponential in the length of n. Thus, trial division works well only if n is very small or happens to have a small prime factor. When it works, trial division has the advantage that it not only determines whether n is prime or composite, but also determines one of n's prime factors if n is composite. In this section, we are finding out whether a given number n is prime. If n is composite, we are not concerned with finding its prime factorization. Computing the prime factorization of a number is computationally expensive. It is perhaps surprising that it is much easier to tell whether or not a given number is prime than it is to determine the prime factorization of the number if it is not prime. Pseudo-primality testing. Consider a method for primality testing that almost works and in fact is good enough for many practical applications. Later on, we shall present a refinement of this method that removes the small defect. Let Zn plus denote the non-zero elements of Zn. Zn plus equals 1, 2, it goes up to n minus 1 elements. If n is prime, then Zn plus equals Zn star. N is a base 2 pseudo-prime. If n is composite and a power n minus 1 equivalent to 1 mod n. As per Fermat's theorem, if n is prime, then n satisfies equation a power n minus 1 equivalent to 1 mod n. Thus, if we can find any a belongs to Zn plus, such that n does not satisfy the above equation, then n is certainly composite. Surprisingly, the converse almost holds, so that this criterion forms an almost perfect test for primality. Test to see whether n satisfies the above equation a power n minus 1 is equivalent to 1 mod n for a equals 2. If not, we declare n to be composite by returning composite. Otherwise, we return prime, guessing that n is prime, when in fact, all we know is that n is either prime or a base 2 pseudo-prime. Following figure shows the procedure pretends in this manner to be checking the primality of n. Assume that the input n is an odd integer greater than 2. This procedure can make errors, but only of one type. That is, if it says that n is composite, then it is always correct. If it says that n is prime, however, then it makes an error only if n is a base 2 pseudo-prime. How often does this procedure error to make a mistake? Surprisingly rare. There are only 22 values of n less than 10,000 for which it errors. The first 4 such values are 341, 561, 645 and 1105. We won't prove it, but the probability that this program makes an error on a randomly chosen beta bit number goes to 0 as beta implies infinity. If you are merely trying to find a large prime for some application, for all practical purposes, you almost never go wrong by choosing large numbers at random until one of them causes pseudo-prime to return prime. But when the numbers being tested for primality are not randomly chosen, we need a better approach for testing primality. Cannot entirely eliminate all the errors because there exist composite integers n known as Carmichael numbers. The first 3 Carmichael numbers are 561, 1105 and 1729. Carmichael numbers are extremely rare. There are, for example, only 255 of them, less than 100 billion. We next show how to improve our primality test so that it won't be fooled by Carmichael numbers. The Miller-Robin randomized primality test. The Miller-Robin primality test overcomes the problems of the simple test pseudo-prime with 2 modifications. It tries several randomly chosen base values instead of just one base value. While computing each modular exponentiation, it looks for a non-trivial square root of 1 modulo n during the final set of squarings. If it finds 1, it stops and returns composite. The pseudocode for the Miller-Robin primality test follows. The input n greater than 2 is the odd number to be tested for primality and s is the number of randomly chosen base values from Zn plus to be tried. The code uses an auxiliary procedure, witness, such that witness of a, n is true if and only if a is the witness to the compositeness of n, that is, if it is possible using a to prove that n is composite. The test witness of a, n is an extension of but more effective than the test a power n minus 1 not equivalent to 1 mod n that formed the basis using a equals to for pseudo-prime. We first present and justify the construction of witness, and then we shall show how we use it in the Miller-Robin primality test. Let n minus 1 equals 2 power t u, where t is greater than or equals 1 and u is odd. That is, the binary representation of n1 is the binary representation of odd integer u, followed by exactly t zeros. Therefore, a power n minus 1 is equivalent to a power u, the whole power 2t into mod n, so that we can compute a power n minus 1 mod n by first computing a power u mod n and then squaring the result t times successively. The following figure shows the pseudocode for witness of a, n to compute a power n minus 1 mod n. This pseudocode for witness computes a power n minus 1 mod n by first computing the value x0 equals a power u mod n in line 2 and then squaring the result t times in a row in the for loop of lines 3 to 6. By induction on I, the sequence x0 it goes up to xt of values computed satisfies the equation xi is equivalent to a power 2i into u mod n for I equals 0 to t, so that in particular xt equivalent to a power n minus 1 mod n. After line 4 performs a squaring step, however, the loop may terminate early if lines 5 to 6 detect that a non-trivial square root of 1 has just been discovered. If so, the algorithm stops and returns true. Lines 7 to 8 return true if the value computed for xt equivalent to a power n minus 1 mod n is not equal to 1, just as the pseudo-prime procedure returns composite in this case. Line 9 returns false if we have not returned true in line 6 or 8. If witness of a, n returns true, then we can construct a proof that n is composite using a as a witness. If witness returns true from line 8, then it has discovered that xt equals a power n minus 1 mod n not equals 1. By Fermat's theorem, if n is prime, that a power n minus 1 equivalent to 1 mod n for all a belongs to Zn plus. Therefore, n cannot be prime. And the equation a power n minus 1 mod n not equals 1 proves this fact. If witness returns true from line 6, then it has discovered that xi minus 1 is a non-trivial square root of 1 modulo n. Since we have that xi minus 1 not equivalent to plus or minus 1 mod n, yet xi not equivalent to xi minus 1 square is equivalent to 1 mod n. If find that the call witness of a, n returns true, then n is surely composite and the witness a, along with the reason that the procedure returns true, provides a proof that n is composite. At this point, we present an alternative description of the behavior of witness as a function of the sequence x equals x0 up to xt, which we shall find useful later on when we analyze the efficiency of the Miller-Robbin primality test. Note that if xi equals 1 for some 0 less than or equals I, which is less than t, witness might not compute the rest of the sequence. If it were to do so, each value xi plus 1, xi plus 2, it goes up to xt, would be 1. And we consider these positions in the sequence x as being all ones. 4 cases. Case 1. X equals, the sequence goes up to d, where d not equals 1. The sequence x does not end in 1. Return true in line 8. A is a witness to the compositeness of n by Fermat's theorem. Case 2. X equals 1, it goes up to 1. The sequence x is all ones. Return false. A is not a witness to the compositeness of n. Case 3. X has the elements minus 1 and the sequence goes up to 1. The sequence x ends in 1 and the last non-1 is equal to 1. Return false. A is not a witness to the compositeness of n. Case 4. X contains the sequence goes up to 1, where d is not equals plus or minus 1. The sequence x ends in 1, but the last non-1 is not 1. Return true in line 6. A is a witness to the compositeness of n, since d is a non-trivial square root of 1. Examine the Miller-Robbin primality test based on the use of witness. Again, we assume that n is an odd integer greater than 2. The procedure Miller-Robbin, shown in below figure, is a probabilistic search for a proof that n is composite. The main loop beginning on line 1 picks up to s random values of a from Zn plus line 2. If one of the a's picked is a witness to the compositeness of n, then Miller-Robin returns composite on line 4. Such a result is always correct by the correctness of witness. If the Miller-Robin finds no witness in S trials, then the procedure assumes that this is because no witnesses exist and therefore it assumes that N is prime. We shall see that this result is likely to be correct if S is large enough, but that there is still a tiny chance that the procedure may be unlucky in its choice of A's and that witnesses do exist even though none has been found. To illustrate the operation of Miller-Robin, let N be the Carmichael number 561 so that N minus 1 equals 560 is equals 2 power 4 into 35, T equals 4 and U equals 35. If the procedure chooses A equals 7 as a base, witness computes X naught equivalent to A power 35, which is equivalent to 241 mod 561, and thus computes the sequence X equals 241, 298, 166, 67 and 1. Thus, witness discovers a non-trivial square root of 1 in the last squaring step, since A power 280 equivalent to 67 mod n and A power 560 equivalent to 1 mod n. Therefore, A equals 7 is a witness to the compositeness of n. Witness of 7, n returns true and Miller-Robin returns composite. If n is a beta bit number, Miller-Robin requires big O of S beta arithmetic operations and big O of S beta cube bit operations, since it requires asymptotically no more work than S modular exponentiations. Quadratic residues. Given a number A such that GCD of A, P equals 1, A is called a quadratic residue if X square equals A mod P has a solution, otherwise it is called a quadratic non-residue. The problem of finding out whether a number is a quadratic residue or not. Problem of finding square roots modulo P is hard, and we still don't have any efficient solution for it. Before we start proving properties of quadratic residues and non-residues, let us introduce a notation shown in below figure. In above notation, A by P is known as the legendary symbol of A modulo P. The legendary symbol is a number theoretic function, A by P, which is defined to be equal to plus or minus 1, depending on whether A is a quadratic residue modulo P. We are interested in finding out when it is 1 and when it is minus 1. The following theorem gives a very simple criteria to check whether a number is a quadratic residue or not. Theorem 1. A number A with GCD of A, P equals 1, where P is an odd prime, satisfies as shown in below. Note 1. A power P minus 1 equals 1 by Fermat's theorem. So, A power P minus 1 by 2 is the square root of 1 modulo P. There are only two square roots of 1 modulo P, 1 and minus 1. Proof. If A is a quadratic residue, then there exists an X such that X square equals A mod P. Taking power, 1 equals X power P minus 1, which is equals A power P minus 1 by 2 mod P equals A by P. Hence, one direction is easy. For the other direction, if A is a quadratic non-residue. Problem. For every 1 which is less than or equals S, less than or equals P minus 1, there exists a unique T, St equals A mod P. Clearly, S not equals T, otherwise A will become a residue. This implies that the numbers 1 up to P minus 1 can be divided into P minus 1 by 2 pairs such that every pair multiplies to A modulo P. Taking the multiplication over all elements between 1 and P minus 1 are shown in below. Using Wilson's theorem, if A is a quadratic non-residue, then A power P minus 1 by 2 equals minus 1 mod P, which is equals A by P. Theorem 2. For two numbers A and B, both co-prime to an odd prime p as shown in below. This is known as the multiplicativity of Legendre symbol. Quadratic reciprocity. Because of multiplicativity of Legendre symbol, it is important to find q by p where q is a prime. This is a hard question. We don't know the answer to it yet. Still, a beautiful theorem by Gauss called quadratic reciprocity gives the relation between p by q and q by p. The first step is to prove Gauss's lemma. Lemma 1. Suppose the number of elements in set S greater than p by 2 is L, where S equals A, it goes up to p minus 1 by 2 into A. Every number in S is considered modulo p, then A by p equals minus 1 power L. Proof. Remember that the set A, 2A, it goes up to p minus 1 into A, is a permutation of elements 1, 2 up to p minus 1. If we consider the first half of this set, S, which is shown here, this is almost the permutation of elements. Say R1 up to Rk be the elements in S less than p by 2 and S1 up to Sl be the elements greater than p by 2. Then the set has all elements between 1 and p minus 1 by 2. S dash equals R1 up to Rk, p minus S1 up to p minus Sl. Problem. Show that no two elements are the same in set S dash. So, the set S dash is just a permutation of 1 up to p minus 1 by 2 elements. Multiplying all elements in S dash modulo p is shown in below. Notice that Ri dash into S and Si dash into S make up a set S, which is shown below. This proves that A by P equals A power P minus 1 by 2, which is equals minus 1 power L mod P. This lemma will help us in proving another characterization of Legendre symbol. Theorem for an odd A co-prime to an odd prime P is shown in below figure. Problem 2. What will be the corresponding theorem when A is even? Now we are ready to prove the celebrated quadratic reciprocity theorem. Theorem 4. For two odd primes P and Q as shown in below figure. Conclusion. In this chapter, we have covered the following in detail. Information theoretic argument, adversary argument, P and NP, NP completeness and reduction, primality tests, quadratic residues, applications to cryptography, lower bound theory, and information theoretic bounds.